student volunteers to kindly intimate the crowd outside, just to tell them that we are going to start the sessions very soon. So kindly call them inside. Okay. I request all the audience members to kindly settle down. We are soon going to start our keynote lectures. I earnestly request all audience members to kindly settle down. It's the event that we have all been waiting for, the keynote lectures. Today, as a part of the inaugural function, we have with us the torchbearers in the field of mining and tunnel engineering. Please welcome Professor Nick Barton and Professor Debashish Dev with a huge round of applause. I request Professor Barton and Professor Dev to kindly take the seats on the dais. I request Dr. Agarwal, Conference Chair, to felicitate, to welcome Professor Barton with a bouquet. I request Dr. Lokhande, the Conference Chair, to kindly welcome Professor Dev with a bouquet. Although they require no introduction, I would like to mention their achievements as it serves as an inspiration for all of us. It is my great pleasure to welcome Professor Barton to deliver the inaugural keynote address. Professor Barton is truly a global citizen as he has consulted on numerous mining and tunneling projects. He has developed the Q system for rock mass classification. He has also pioneered the Barton-Bandis shear strength criterion for rock joints, which has been incorporated in UDEC BB since 1985. He has given the QTBM prognosis method and Q slope method as well. With over 280 publications and more than 40,000 citations, Dr. Barton has received several international awards, including the much acclaimed ISRM Mueller lecture in 2012. He is truly the embodiment of the phrase, once a scientist, always a scientist, and he is still consulting on projects in several countries. I now request Professor Barton to kindly address the gathering with his keynote lecture titled Tunneling, Mining and Rock Slope Analysis Using Q Parameters and JRC-JCS Parameters in place of Huckenbraun and the repeating GSI. Professor Barton.
So thank you very much for the kind introduction and also being invited here in the first place. It's a pleasure to be in Nagpur, yeah? I have been once before. So I understand that I will have a little bit more than the half an hour that I had planned, so I can go a little bit more slowly, which will be good. The screen is very stretched, so some of the figures are not exactly as I'm expecting to see them. So you see the title. I could have made the title like Q or GSI. Occasionally, that's the title that I've used, but this title is giving me a little bit more room to show you several different projects, not just is it Q or GSI. So those will be the sort of keywords that you keep hearing. A lot about tunnels, caverns, Q value. I don't know if I need these really. Do I need this? Isn't it disturbing the sound? It's better without these, yeah? So is it better now or not? Yeah. So I'll show some interesting collapses which give us some ideas about things we should think about when designing tunnels and caverns. Towards the end, there'll be a little bit about slopes, how we model slopes, and all the way through joints, because mostly rock masses have joints and maybe minor faults, and to ignore them is not really a good idea, yeah? Although it makes life simple, of course. So the Q system is a very wide numerical scale, 10⁻³ to 10+3. The Sugarloaf Mountain on the left is like a quality of 1,000, perhaps. It should be at least twice as high as that, but this screen is stretching everything and making people look fat, yeah? So the Sugarloaf looks fat also. The quality there, you can see the parameters, it's maybe 1,000. And the serious fault zone with swelling clay on the right is also in Brazil. There were 3 like that in a tail race tunnel, and each of them blocked the flow of water, actually. So we had to visit in a rubber dinghy in a boat between the places that were blocked. So the wide numerical range of Q, it reflects the huge potential range of rock mass properties. Some people feel uncomfortable with that. They like the 9 to 95 RMR GSI sort of range, but I think that having this huge range, it makes it easier to develop simple equations between parameters and the Q value. So Q or GSI, you'll see in a moment that you might know this publication, Ehrharter et al. It's about 4 or 5 authors. Some of them are from the countries that responded with the questionnaire, which is the most common classification methods you use for the underground or for rock slopes, from mining or civil engineering. And the Q system, you'll see, is now apparently the most commonly used for the underground, civil and mining, with maybe quite a big majority. RMR is next, I think. And then GSI is the most widely used for surface and slopes. So the purple color is the Q. And the blue, if we look at India there, we can see there's nearly the same amount. I'm sorry that I can't point to this. Let me just try once more in case, but I have a strong laser, but I think it doesn't work, yeah. So if you look at India, you see there's half of it's purple, or a third of it's purple, a third of it's RMR, and then some other methods as well. The GSI one, if I showed slopes, you'd see a lot more of the green, which is GSI, yeah? So I usually show a picture like this, which is nice rock mass exposures and some core boxes from different countries in the world. And I use this to mention that we cannot take rock mass samples. I mean, if we're really clever Chinese people, they seem to be able to saw rock masses into pieces and bring it and make an ornamental kind of a rockery around an expensive hotel, and even with a waterfall, but we can't do that. It's much too expensive. We can't bring samples into the laboratory like we can with steel or concrete or soil. So Q saves us from impossible sizes of in situ testing. We can get numbers just by looking and characterizing the rock mass, and those numbers we can use in various different ways, and you'll see some of them today, of course. So for those of you who perhaps are using RMR more than Q, perhaps it's helpful to see right from the beginning, we use Q when we come down into the jointed rock. We can sort of get some numbers in the orange, which would be the saprolite, the very, very deeply weathered. But it's more reliable when you have joints, because a lot of the parameters, that's why the symbol J is used so often, yeah? So it's RQD divided by number of joint sets, that's like block size. JR over JA happens to be like a friction coefficient. The case records gave that. It wasn't my idea. The case records gave it from the ratings that were necessary. And then something I call active stress. So I'm going to show just a quick glimpse of some Q parameters, but maybe in a little different way than you've seen them before. First of all, RQD, that's regular, yeah, and then especially concentrate on a ratio, JN over JR, which is to do with overbreak. JR-JA, you're probably aware, obviously, of the friction coefficient idea. And then SRF for high stress, maybe a different way to look at it than you're familiar with. So these are the statistics from 40 kilometers, 40 kilometers of core logging at a gold mine in Colombia. The engineering geologists there, I think there was like 12 up to 15 of them, they logged actually 340 kilometers of drill core. This is the statistics for 40 kilometer. And you see the bell-shaped curve towards the left. That's giving kind of a median value RQD of 50. That's where the Q class is 1 to 4, which we call poor rock in Norway. And some countries, they might say medium rock, yeah? 1 to 4 is quite well jointed. Maybe there's some clay. 4 to 10 is perhaps more common in Norway. But we see the full range in most of our tunnels in Norway, at least. Maybe goes above 100 also. And occasionally below 0.01. So we're looking now at the second and the third parameters, a ratio. JN, the number of joint sets, divided by JR. You see the JR roughness profiles. They should be slightly rougher because the screen has been stretched, but you get the idea, yeah? And the blue ratios on the left, they are when the ratio of parameters is less than 6, so overbreak is not likely. Even the 15 over 3, that's 4 joint sets with the rough joints JR of 3. Maybe that prevents the overbreak because of the dilation, yeah. But on the other hand, on the red numbers, the 15 over 2 and the far right, that's 4 sets with a smooth undulating joints, they can more or less overbreak and cause problems with more volume of shotcrete, more volume of concrete if you're doing NATM. Those 6 photos roughly showing JR of 1 through to at least 3, probably 3.5 is the lowest one. On this scale with the stretching, it's maybe closer to 3, yeah, but originally it would look like a 3.5. So then JR determines the dilation angles. It really determines stability and overbreak and failure if you don't have the roughness, yeah. So the next pair, JR over JA, you're familiar that that's something like friction coefficient, and maybe you've seen these curves here on this table. I'm not sure, but this is a category A rock wall contact. And if you did a direct shear test, you'd get something like the figure in A. So it would have a regular sort of shear strength displacement curve. If there was a bit more clay, then you get the one like B, a little bit softer, and then stiffening when the rock-to-rock comes in contact. And if it was a thick clay filling, you'd get the result would be determined by the mineralogy of the clay, yeah? And it could be even below 10 degree. It could be down to 5 degree in some cases with montmorillonite, for example. So in the table there, I've taken arctan or tan minus 1 JR over JA, the ratio, and it looks like friction angles. But in the top left of the table, they're rather high angles. So it's like phi plus I, phi plus dilation. And in the bottom right, they're rather low values, and that would be like phi minus contraction, phi minus I, yeah, but with contraction because of clay coatings. And it gets worse if you get thicker clay fillings. So this is, very, very much more sophisticated than the scale you have in RMR or GSI, which uses the same scale of joint condition. And here you can have rough joints with clay. In the GSI RMR, apparently you cannot have rough joints with clay and with weathering. So there's some really strange limitations in RMR and GSI if you look carefully at the chart. Here you can choose the combination that you want, yeah? Because there are so many millions of different combinations in practice. So moving on to this fourth Q parameter, and then we'll go to a little bit different subjects. And this is to show, it's actually the sixth table in the Q ratings, 6B. So competent rock stress problems, and you can see some descriptions there that we're moving into rock bursting if the tunnel is deep enough or if the mine is deep enough. And since our paper in '93, we concentrate on the ratio shown with the blue arrow. The maximum tangential stress estimated from Kirsch formula, like sigma, what is it? The maximum tangential stress is 3 sigma 1 minus sigma 3, and the minimum tangential stress is 3 sigma 3 minus sigma 1, yeah? You know that formula, I'm sure. So comparing the maximum tangential stress, sigma theta, divided by UCS or sigma c, when we come to a ratio 0.4, sort of magic ratio, you start to get cracking and fracturing and in the end rock bursting. And you see on the far right, the SRF table starts to accelerate. The SRF rating accelerate very strongly after 0.4, so that you get a lower Q and then a much heavier support for kind of trying to avoid the damage with minor rock bursting and popping. And this 0.4, it actually occurs if you load a sample, a uniaxial sample in the laboratory. When your sigma 1 has reached 0.4 of the final strength, you start to get acoustic emission, actually. But it's not compression failure. It's actually extension failure first, and then maybe shear and final failure. So here is, on the left, there's a numerical model system called FRACOD, F-R-A-C-O-D. Those are TBM tunnels, so you can see how distorted the screen is. Yeah, it's really a pity that everybody has these distorted screens in so many countries. But anyway, So we're also in the circular TBM tunnel on the bottom. And this is the first TBM tunnel that's ever been driven significant distance in 1880, next to the Channel Tunnel. So it's turned under a cliff where there's a 70-meter high overburden. And that's enough to cause this fracturing at sort of, what would we say, 8 o'clock to 10 o'clock and 2 o'clock to 4 o'clock on a clock system. So you get crushing in the abutments due to several megapascal higher tangential stress. Because the rock is weak, it's actually chalk marl, it's only got a compression strength about 4, 5, 6 megapascal. That's what they tunneled in the Channel Tunnel between England and France. So if you look at the red text there, the critical tangential stress, 0.4 times UCS, is actually numerically the same as sigma t, tensile strength, divided by Poisson ratio, nu. And the reason they're the same is that the ratio UCS over UTS, compression over tensile strength, is about ratio 10 to 1, 15 to 1, and Poisson ratio about 0.2, 0.25. So it explains this magic 0.4 plus or minus 0.1. And it comes from that classic equation there for the radial strain, e to 3, yeah? So one should really measure tensile strength and Poisson ratio, not just UCS, but UCS is, of course, easier, yeah? So on the top left is the original case records that I collected to develop the Q system. I've got apparently a bit more time than half an hour, so I can say why the Q system was developed. It was not planned. It came as a result of a question to NGI that just by chance was passed to me. Can we explain why the State Power Board, Statkraft, why the State Power Board power stations have a big range of deformation, like 1 or 2 millimeter up to 150 millimeter? Why? They wanted to know. So I started to collect case records from Norway, from some NGI projects, from Sweden, and I couldn't answer their question. For 6 months, I had to kind of develop the Q system before I could answer the question. So that's the range of case records that you see there, mostly from 0.01 up to, say, 100 is the big range that we see in a long tunnel, yeah? And in 1993, with a huge help from Grimstad, I mean, it's Grimstad's extra case records, more than 1,000. We developed this chart with the thickness of shotcrete, you can see, categories 1, 2, 3, 4, 5, going to the left, yeah? And then the spacing of rock bolts on the top of the diagonal, going from 2.5 down to 1 meter spacing. And there's an area in there. Area 8, if you can see, it's the area where we use this rib-reinforced shotcrete. I'll show you pictures of that in a moment. And area 9 would be cast concrete. So maybe a combination of both when you're coming into a fault zone and you don't get through unless you have concrete lining. In NATM, they'd try to use lattice girder and hope they don't collapse, yeah? Because sometimes the lattice girder fold, and you can see some examples of that a bit later on. Okay, how we collect data. First of all, you see that the 6 Q parameters, they're just part of an engineering geology exercise. If you're going to do numerical modeling for an important project, you want to collect other information about joint spacing, joint length if possible, joint roughness, joint wall compression strength if you're going to use the BB parameters for doing UDEC, and then things about rock permeability, compression strength, and so on. So Q is just part of the story, and it's an important part, and we started to use Q histogram logging around 1990. You'll see the very first version that I did in a mine in northern Sweden in a moment, yeah? So just collecting the statistics of what you see, the RQD, the J, and JRJ. Can you explain overbreak because of those parameters? If you look carefully, there's the description is above each histogram and the rating is below each histogram. So it's kind of a logging sheet with all the ratings that you need. So here we're going to show how the Q histogram operates. If you go down a borehole in the same rock type from the saprolite, the heavily weathered sandstone down into weathered sandstone down into more massive sandstone, going down the same borehole, we're going to just click on character of saprolite and soil. We're going to move to the logged character of the near-surface sandstone, and then logged character of the deeper sandstone. So you see how the RQD is increasing and the JN is reducing, the number of joint sets is reducing. So do that again, 1, 2, 3. So that's much, much more sophisticated than moving across a two-parameter diagram. I think you have to admit that, yeah? The comparison is like night and day, really, because there's this strange characteristic, the surface condition, directly taken from Biniarski, actually. Hook in the GSI chart, he's taken it's on the left there, there's very good, very rough, fresh, unweathered surfaces. So it's implying that you cannot have clay in the rough joints and you're not weathered. But what if they are, yeah? That excludes a whole range of condition. At the far end, it's slickened sides with clay filling and things like that. So it's much, much more flexible if you use JRJA compared to moving across that diagram. So now some useful linkages to Q that you may or may not have seen. Relative cost, relative time, tunnel deformation, Q and P wave velocity, and deformation modulus. So on the left, there are two diagrams showing the complete Q scale from 10-3 to 10+3. And the top one, you won't be able to see it from where you are, but it's a ratio of 12:1. So as you move from very high quality towards lower quality, you don't need any rock sport. And then after, when Q is less than about 10, you start to need rock sports, and the cost goes up. And the one below is relative time. It's a ratio of 10:1. So the cost goes up when you have to start using the shotcrete and the rock bolts, of course. And on the right, I use the Q system to get those cost estimates, relative cost estimates for 50 square meter tunnel, 180 square meter or 90 square meter and 130 square meter. And I've written NMT there in the lower area because that's typical Norwegian method of tunneling type of rock quality range from 0.1 to 100 maybe. If the quality was much, much worse, the NMT lettering would move up and come in the same place as the NAT lettering, which is much higher cost because we'd also have to use cast concrete as the final lining. But NATM is always using the cast concrete, so they're always expensive and taking more time than the NMT. So the cost of NMT tends to be a fraction of NATM, and it goes much faster. But NMT is obviously also costly in bad rock, yeah? The two sets of data on the top left, they're actually from an analysis of about 50 kilometers of contractors' records of tunnels in Norway and also Sweden, some 50 kilometers that were collected by Roald, one of my colleagues. Okay, Q and deformation. So the top diagram, I plotted Q divided by span in meters as a log scale, and on the bottom, the deformation on a log scale. And most of the data is from the Gjøvik cavern that we'll be showing a little bit later, this 60-meter span cavern in Norway. So there were a lot of MPBX there, 7 or 10, actually 10 MPBX in total of data. So there I plotted it. And some years later, some kind colleagues from Taiwan, they sent the very concentrated data from hundreds of tunnels in Taiwan. And I thought, wow, that's really interesting. It seems to stay on this diagonal, yeah? So what's the equation of this central diagonal? And it turns out that it's the very simple delta millimeter equal span in meters divided by Q, the top formula. So, I mean, it kind of demonstrates that Q is quite a powerful parameter if you can have such a simple equation as that. but it's a kind of a moving shotgun plot, so a bit more sophistication, the second or the third equation. And they have span in millimeter divided by 100Q, multiplied by square root of the stress over strength, the vertical stress over strength ratio, competence factor, some people call it. So in these two caverns in Hong Kong, the simple formula, it gives 1 millimeter for cavern X, which has a Q value of 20.5, and cavern Y has a Q value of 7. And we've got the span above, yeah? So just 1 millimeter, 3 millimeter. And then the more sophisticated equation, in this case, it gives the same result. And this is very close to what was measured with the MPBX. So you see the millimeters, 22500 is millimeters instead of 22.5. They're fairly shallow. You see that from the 1.25 to 1.5 vertical stress in megapascal, divided by UCS 125 or 150. Also, Q, or better still, Q sub C. The Q formula normalized by UCS over 100. I started to use this when I was relating Q to velocity and modulus about 20 years ago. And this is an empirical relation, or the curve, the lines are empirical. You see there's a depth correction. As you go deeper, you go above the central diagonal. I guess I can walk here, so it's very difficult not to be able to point to things. So this central diagonal here that you see going up with 25 nominal depth, nominal porosity 1, that's the data for shallow tunnels, and then there's a lot of deep cross-hole seismic tomography for the correction for deeper tunnels. So it's a plus effect increasing VP, and if there's porosity, it's a minus on VP. And on the right, there's a table that shows estimates of deformation modulus. So the key message here is that velocity increases with depth because of the closure of joints, and the modulus also does. So one of the formulae you can use is there, which if you have VP increasing with depth, the red formula, you can see how the EMAS would also increase. And this is in contrast to what you find in rock science software, where they use Hook and Diedrich, or Diedrich and Hook formulae for estimating deformation modulus using GSI. They don't have a correction for depth, which is not correct, yeah? Obviously, modulus increases with depth because joints are more tightly closed. Another recent use, Q and VP have some proximate relation to block size due to RQD in the number of joint sets. So if you're looking for quarried rock with very large blocks for a marine construction, a naval port or something like that, you can actually have some idea that you can estimate block size using Q. So there you see in the boxes possible ranges, likely ranges of the weight of the blocks for the different Q value and different VP. And when you get up to QC of about 100, 3 to 6 ton blocks, more than 10-ton blocks, then you've got so few joints that you need to do some smooth wall blasting maybe to kind of cut the rock mass into blocks for the really large blocks of 2 or 3 cubic meters. This is seismic tomography, again talking about correction for depth. This is seismic tomography, one of the sets of data for the Yervik cavern, in this case between 2 vertical boreholes, about 50, 60 meters deep. And you can see the velocity increasing from the surface, like 3.2. That's a Q value of about less than 1. And it's really fractured rock, yeah? And if you get into the lighter color, it's 4.9, nearly 5 kilometers a second. So the strange thing is that when you go down one of these boreholes, the RQD is just varying up and down around 80 to 90 to 100. And the joints per meter on the bottom is just varying between a few joints per meter. There's not a trend for increasing spacing with depth, right? And the RQD is not improving with depth. And the Q value is also not improving with depth. It looks similar to the joints per meter result, except it's like between 5 and 25, going like this, not increasing with depth. But the velocity is increasing 2 kilometers a second with depth, just because of the stress closing the joints. So modulus has to be corrected also because of depth. So in the geometry for our Gjøvik cavern, stretched out rather a lot, you see the moduli that we use, 20, 30, 40 GPa, going down with depth. I made this geometry from observations in local caverns, and the larger blocks at the base are just for convenience and less computer time, but the modulus is according to the numbers that you see. And you see there are some extra caverns there to the right. They were ordered while the contractor was still on the site, because it was going very well, making the big caverns, so they wanted to have some more caverns, actually, for the post-service. And the biggest one is 20-meter span, so quite a big cavern, the number 7. So we were a little bit worried. We did the modeling for the Gjøvik cavern first, and then what's going to happen if new tunnels, the new caverns, are going to be kind of eating into the stress arch that is helping to support the first cavern. So there was an increase of 1 or 2 millimeter and a little bit extra load on some of the bolts in the pillar area. So you can see the estimate for the horizontal stress was quite significant compared to vertical. So it was a positive high horizontal stress in this case. So we'll come back to Gjøvik a little bit more and show some UDEC models later on. Okay, tunnels for civil engineering. Do we choose single shell, what we call NMT? Because if you're using Q, we take the liberty to call it Norwegian method of tunneling, because it's with Q, and you get the design of how much shotcrete, how much rock bolt. So we coined the phrase NMT just as direct competition to NATM, because we felt we were doing something different in Norway, much cheaper than NATM. So it's an economic single shell or costly double shell as alternate tunneling methods. So number 1, the single shell NMT, mostly bolting and fiber-reinforced shotcrete, and maybe the RRS, the rib-reinforced shotcrete, that I'll show a picture of in a moment. And we have a much, much smaller workforce. You just see 2 or 3 guys at the tunnel face with a big drill jumbo or with the shotcrete robot. And the NATM double shell, there's temporary support like shotcrete or mesh-reinforced or fiber-reinforced, and bolting and steel sets or lattice girder. That's apparently considered temporary support, and it's not taken credit for extraordinarily. So the thing they take credit for is the final concrete lining, maybe with the reinforcing steel, yeah? And the permanent part is also the drainage fleece and the membrane. So a much, much bigger workforce, 10 times more, maybe 20 times more, depending which country and what the cost of labor is. So I'll show each of the operations with diagrams. NMT operations as an initial summary, those 3 components. So we've got the drilling, the mucking, the pigging or scaling. Q-logging in the middle. We have something called the owner's half hour in Norway the last 20 or 30 years. So an engineering geologist representing the owner, which is maybe the designer, and an engineering geologist representing the contractor. They go up in a basket under the tunnel arch, the new tunnel arch, and they log and they try to be in agreement which rock class we're in now. Is it Q1 to 4 or whatever? And there's a pre-designed rock support, rock reinforcement for that particular class. So there's a nice record, a good record, usually agreed record, sometimes not, between the 2 different sides. And then the robotic shotcrete comes, and then the bolting. And if it's a tunnel that's going to have high traffic, we have a PC element liner, freestanding PC element liner with a membrane on the outside. You'll see a picture of this in a moment. So the NMT tunnel, the first layer of shotcrete and the bolting you see in the top left. It's a tunnel that's been pre-injected. It's a high-speed rail tunnel. And the steel fiber reinforcement is just like in the diagram from Van der Waal, the guy who is responsible for the Dramix fiber from Belgium, the one with the little, looks like a little bridge, yeah? The steel, cold-drawn steel. The mesh reinforced in the green, that's not advised because you get electrolytic corrosion and you get shadow, and it's not nearly so reliable as long-term support. So the diagram is very realistic, I think, on the middle. The CT bolt is sleeved bolt, a PVC sleeve, different colors over the years, and there's grout in the inside of the sleeve and grout on the outside. And obviously the bolts can be 2, 3, 4, 5, 6 meter long. This is just a demonstration length to show there's wedge anchoring, and the grouting can come later, yeah? And you see there's a diagram, or a photograph in the middle, bottom middle, with a blue circle. That's the PVC around the bolt that's been cut. And there's a crack, a joint, and the joint is maybe moved when there's blasting, because you put the rock bolts close to the face. And that comes and it cuts through the outer annulus of grout, right? So that would be the start of corrosion of a regular bolt. You've invited the water into the bolt. But these bolts, they have a PVC sleeve and then another grout, and then they have epoxy painting and galvanizing. So there's 4 more layers of protection. So they're like a 1,000-year bolt, not a 120-year bolt, yeah? They're really permanent bolts. They're more expensive, obviously. The RRS looks like this. It's in that area with the blue arrow. The dark purple is the cast concrete. We'll look at this picture is a bit bigger scale. So the RRS looks like this. So it's a bundle of 16 millimeter bars that can be bent into a big overbreak. We're not relying on a perfect circular lining. You can bend the bars. The key thing is that they're systematically bolted, 1 meter spacing with 4 or 5 meter long bolts. So the very poor quality rock, it gets the bolting it needs, and it gets this bolted lattice girder, but something much, much stiffer than the lattice girder, because it's not going to move like a lattice girder does. And you can bend it into the shape required by the architects, or you can bend it into overbreak. It takes more time, but at all stages, it's more support of the concept that rock is the construction material. You're reinforcing the rock mass. The rock mass is going to take the thousands of tons of tangential stress, not the lining, yeah? And this is a full, complete sort of RRS chart and shotcrete chart from Grimstad. And you take the left side of these boxes. So the one with the blue arrow, the left side is at a Q of 0.004, really, really bad rock, clay, and water, very low friction strength. And the solution is 45 centimeters. It's the double layer of the bars, and 45 centimeter thickness, 6 bars, double, and spacing of these arches of 1.7 meter, yeah? So you get actually a sort of a 3D effect because of the arches next to each other gives you a sort of 3D extra support capacity. These are pictures from more than 30 years ago from a contractor's brochure showing the shotcrete robots by a company called AMV, Anders Mekaniske Verksted, it's called, Anders Mechanical Workshop. So they make wonderful tunneling machines for a long time. And you see the operator is halfway up the boom so they can see the work that they're doing, much better than standing on the floor and trying to see if the shotcreting is doing well 20 meters above. Yeah, you can be way up the boom and see what sort of work you're doing. And they can spray 15 up to 25 cubic meter of shotcrete per hour, yeah? So they're really good for big tunnels and caverns, cavern top headings. This is one of the lorry turning cables in the longest road tunnel in the world, the Lærdal Tunnel. Grimstad had a lot to do with recommendations for the support there on behalf of the road authority. And you can see a car there, so the tunnel, the lorries can, even the articulated lorries, they can come in and they can turn around here. And actually, some people say that in the winter, there are some lorry drivers, they sleep in these caverns, they sleep in their cabs, because there's almost no traffic in the winter, and there's plenty of space to park there. So they're very deep, they're from 1,000 meter up to 1,400 meter, these 3 turning cavern. And they're actually a beautiful color. You don't see a sort of pink, greeny color. They kind of wake you up if you're going to sleep going kilometers along this tunnel. So again, it's been stretched out, but this is the PC element liner. Freestanding, the rock mass has been supported with Q system, and it's shown a little section of bolted rock there with the joints and the shotcrete. Then there's an air gap of something like this, wide enough to have inspection if you want. And then the 4 PC elements bolted with a dotted line representing the membrane on the outside. So in this case, you're letting the water drain towards the tunnel and you're collecting the water, but the tunnel surface is dry, whether this is rail or road, yeah? And maybe there's insulation of the PC elements. If you're in a few hundred meters of the opening and you're in the winter in Norway, you're going to get frost, so this prevents the icicles forming. So now NATM in a nutshell. This is from a diagram from the Austrian Society. I think it's 2010. And some contractor has colored, so it looks a little bit nicer with the color. The top heading you see along the top, and then the benching down and the very significant shuttering you have to make for the cast concrete on the bottom right. And I mean, it all looks very nice and beautiful, but what about overbreak? What happens if you have overbreak? How does it affect NMT? How does it affect NATM in relative terms? So we can draw a line with not in any way exaggerated overbreak. We could make it double as we could make. I've seen overbreak 2 to 3 meters in some big tunnels, but usually, of course, it's less than half a meter. But overbreak is going to make you a larger volume of shotcrete. In the end, you have to fill that void with shotcrete or concrete if you're doing NATM. And it's going to affect how the lattice girders make good contact with the rock or not. So it's all increasing the effort of the contractor and his bill if the rock has not been described very well. So actually, there's some contractors who've won court cases because the overbreak parameters were not sufficiently described. 2 court cases in Hong Kong I know about where the contractor was compensated for much larger volume of shotcrete and concrete because of overbreak. So again, the beautiful NATM section, nobody ever shows overbreak, the designers. Maybe they don't dare to, but the reality is there might be overbreak. This is a tunnel in Sweden using NMT because they use Q systems, so we call it NMT, not SMT, yeah? Not Swedish method. They use Q system and they use shotcrete and rock bolts. A lot of overbreak in this section, and it's ready for the tracks to be laid. So this very ununiform shotcrete is fantastically stable, wonderful bonding, and systematically bolted. The bolts are sprayed over. So, I mean, that tunnel on the right is probably more stable than the tunnel on the left because the rock mass has really been well reinforced and preserved, better than in an ATM tunnel. Okay, a little glimpse of mining. This is from the LKAB Kiruna mine in northern Sweden, one of the largest underground mines in the world. And they had a project there, a long-hole drilling project called the Oscar project, and they wanted me to go in and try to explain using Q parameter why there was such very big overbreak and nearly collapse of the top hole drilling galleries and some of the draw point galleries as well at the bottom. So I've sketched in what the overbreak looked like sometimes. I sketched in the big scale J1, J2 joints. They were worried if a whole stope could be blocked by a major block movement, right? When they saw what was happening in the smaller tunnels. So there you see maybe the first sort of Q nearly histogram, RQD, JN, JR, JA. The most frequent JN over JR is 9 over 2, which is 3 sets and smooth undulating, and that's less than 6, so it doesn't describe the overbreak. But if you go to the extreme, if you take JN of 12 to the right of the green, and you take JR of 1.5 to the left of the red histogram, then you're getting 1.5 over 12, that's already 6. And if you add a bit of bad JA, you can explain the overbreak, right, with those parameters. So it's kind of convenient. It's so different world than using GSI and continuum modeling. I mean, it's like night and day again, yeah? So control of water in NMT and NATM. We do a lot of pre-injection in Norwegian cities because they're often in an area where there's been marine clay, and you have to prevent the groundwater drawdown in the marine clay. Otherwise, you're going to get damage to buildings. And there have been some cases, I mean, there's a case, you'll see a photograph of a tunnel, Stockholm bypass, where they had damage like out to half a kilometer on each side. A football stadium was damaged. A lot of houses were damaged by differential settlement because the pre-grouting was not done well enough. So in Norway, we've done lots and lots of pre-grouting. We used to make a lot of mistakes like 40 years ago, and it got better and better 20 years ago, and now they can have like 1 or 2 liter per minute per 100 meter inflow, and that more or less prevents the drawdown of the groundwater. If you go like 4 to 10, then you're going to get some damage. 10 and above, 10 liters per minute per 100, you're going to get damage. So you see the umbrella, you see about 70 holes in this big high-speed rail tunnel. It should be much more like an arch. It's been squashed out. And there you see the last 70 or 80 meters in that tunnel. I think they're doing a post-injection of 1 leaking hole. But basically, it's sort of dry shotcrete if you do the job properly. So there I've written 99.99% dry shotcrete due to successful pre-grouting. And the next picture is 99.99% wet shotcrete, a dark, kind of a strange dark color. And there are just a few areas on the right, a little bit lighter shotcrete. You can see nearly at the edge of the photograph. That's dry shotcrete. So the Swedes, they're not using high enough injection pressure. They're only injecting 1 joint set. There's water coming in, and the 2 or 3 joint sets that are not properly injected. So a huge amount of environmental damage. And in NATM, just to show some difficulties, if you have overbreak, if you haven't already filled the overbreak with more shotcrete, cheap shotcrete, yeah, then you're going to have a big difficulty fixing the drainage fleece and also difficulty with the membrane outside that before the concrete comes. And this really surprised me when I looked in this tunnel which had the white membrane, and I saw the spacing of the welding seams. I think it was 1.5 meter. So you could estimate that you had between 12 and 15 kilometer of welds per 1 kilometer of tunnel that had to be perfectly welded, yeah? If you had a leakage, you wouldn't know where the leakage came from because it could come out from the concrete 30 meters away. You wouldn't know how to repair it. Okay, lessons from 2 collapses. Number 1, a tragic shallow cavern case record from Brazil. So just the text in the middle here, it says, question, should we have a shallow metro or a deep metro? Shall we have mixed face or rock? Shall we progress 5 meters per week or maybe 20 meters per week? And the cost difference might be 5 to 1, at least. And it's kind of a potential choice between NMT if it was deeper and NATM if it's shallower. So the very shallow escalator that they wanted in Brazil is top right photograph, a much deeper escalator typical in London, in Prague, and other places to get into the good geology for a tunnel metro is shown in the second photograph on the right. And the NMT tunnel would be the bottom right, yeah? So let's have a look at what happened here. So this is a very nice drawing from a geologist called Linton, an English geologist who was explaining the origin of tors, T-O-R-S, towers of rock. I've put to the Q value. So where there's lots of joints, maybe Q is 10. Where there's very few joints, Q is 100. And after a long time of weathering, you get the saprolite and the deeply weathered granites, for example, the black color, maybe it's Q.01. So imagine that you have a tunnel project or a cavern coming along under here, and you're not aware of this big load of rock that's coming above you if you've missed it with drilling, yeah? Are we okay for time? The time is okay? Yeah? 5 minutes more? Okay. So this, usually in the city's on the top of that clay, yeah? If it's not, you might see it like that in some countries. In southwest England, the tors are like that. In this particular case, there was you see a blue line on the top there and a blue line coming down. That's where there was a borehole in this project. So they missed this tower of rock, and the lattice girder got crushed. And unfortunately, I think it was 7 people that lost their lives. They were sucked into the collapse. So they thought they had the picture on the left, 3 meters of rock overburden. The reality was they had a ridge of rock 10 meter high, and it fell 10 meter after it crushed the lattice girder. They missed it because one of the boreholes was in a fracture zone. So that's what happened to the lattice girder, 32, 25, 25 millimeter bars. So not so strong as it looks. It kills you if it falls on you, but it doesn't resist a big vertical load very well. Those are the results of experimental tunnel in mudstone from England a long time ago, and they're a very nice demonstration of the rock bolt and shotcrete, how successful that is, yeah? And then sprayed concrete arch, just rock bolts and just steel sets, bigger and bigger deformation. So the B plus SFR solution is reducing radial deformation. If you only have bolting or only steel sets, you're inviting SRF increase. So steel sets and lattice girders, they allow or they invite, they actually require loosening of the rock mass before they start to work, because you have to have the footing not deforming anymore, and you have to have resistance to point loading, maybe, not very good contact with the rock. So there's their own deformability to build up tangential strain in the steel, and finally, maybe some radial resistance. So the lattice girder that you see on the left being installed, it's exactly the same lattice girder that you see there that collapsed later because of this rock load. The central photograph, it's fallen already 10 meter. Everything has fallen down to the bottom of the cavern. And you see this kind of pack of cards. That's what the rock looked like in the top of the ridge of rock that nobody knew was there, yeah? They should have done cross-hole tomography. Then they would have found it. So the second case, a twin motorway tunnel with light, inadequate temporary support and anisotropic challenges. So the first terrible error, the lack of excavation of soil and saprolite in the portal area. This is a no-no, yeah, obviously. They were cutting some corners there. And there was light lattice girder. The designer assumed isotropic condition, horizontal surface. All that was incorrect. They should have assumed the curved surface and makes a much larger deformation. Some models from Bandis. And when a vertical load from phyllite is added and a vertical dike, you start to see the progressive failure of the right-hand tunnel. And a 3-deck model, the progressive failure. And luckily, there was a barbecue. It was Saturday afternoon, and all the tunnel workers were having a barbecue. Otherwise, there would have been terrible fatalities in this project, because 140 meters of the tunnel was lost. A few months later, the other tube, another 140 meters, also collapsed. And this is what the surface looked like, with like rotation of the telegraph poles and things. Okay, a little bit of critique now. The equations for GSI, the equations for shear strength, C and phi, Hook-Brown equations, they use GSI. And those of you who are using rock science software, you just punch in the numbers and you don't think anymore. If you substitute those three equations and one more, you find that C and phi, they have GSI repeated a total of 78 times. GSI is repeated 78 times in the equation for shear strength. Does that sound sensible? I don't think so. I don't know. Is there any other subject in the world that would accept that sort of error, yeah? There's that uncertainty, you could say. So Hooke himself, he was concerned about better quantification of GSI. So most of these equations are from Hooke, actually. And if GSI was improved, what would happen to C and phi? One could also ask, yeah? So these equations, do we really want rock engineering to consist of these equations, yeah? What about modulus? You can choose any modulus you want if you have a different range of the disturbance factor D. It's not very convincing rock engineering, really and truly. So actually, if you cut the Q formula into half, you can get some equivalent formulae, a little bit crude, but you get an approximation from half of Q and half of Q for C and phi, compared to like 30 and 40 times GSI and the other equations. So BB parameters for input to UDEC BB so that joints can be modeled. So the third equation, the blue one, is the one I developed from a lot of direct shear tests. You'll see a little glimpse in a moment. And then we can ask what we learned from a continuum model like FLAC, a wonderful model, but it's not including joints and faults. And the UDEC model, which gives more anisotropic behavior. So those are the shear tests that we did a long time ago in NGI to get the range of JRC JCS for 7 different rock types. And there's no cohesion. If you see down at the axis, there's no actual cohesive strength. And we did the tilt tests. Those 10 samples, they're actually the origin of the 10 curves, the 10 roughness profiles that were just showing what we'd been testing. And thanks to Bandis, there was the concentration on the effect of block size. What's the spacing of the cross joints? Is it 0.5 meter, 1 meter, 2 meter? You have to scale JRC and JCS because of the block size. And roughly speaking, a lot of rock masses, maybe the great majority, they're between Q value 0.1 and maybe 100, and they're UDEC or 3DEC or some equivalent codes today that really have joints. They're the appropriate thing to use. So very quickly, 5 examples of UDEC BB modeling of tunnels, so you can really feel that you're putting in some geological data there. Stresses, shear displacement, and deformation. Stresses, shear displacement, and deformation. And a tunnel in Japan that's showing very high loads in the horizontal bolting, and some shotcrete distress, some shearing. The dotted lines in the central diagram is some shearing. Some of the shotcrete has even come away from the tunnel wall. This is a coupled case where you have, even though a two-dimensional model, we're modeling water flow. So water drawdown, the blue, and the red is the shearing during excavation, and the blue on the shallowest joints is the amount of water coming into the tunnel. This is a combination of UDEC and 3DEC. So in Japan, they used a TBM to do like a pilot tunnel from the different lanes of the motorway. Early UDEC studies, low horizontal stress, intermediate horizontal stress, high horizontal stress. The reality was somewhere in the middle between 2 and 3. So you see the first stage of excavation, the top heading on the right there from UDEC BB. And then you see top left, one of the big caverns has been excavated, and it had some effect. So now the deformation is like 7 or 8 millimeter, and it's very close to what the MPBX show. The one in the middle is something that really disturbs me. It's a geoscience, sorry, what are they called again? rock science. It's a rock science code with pseudo-jointing, and these joints can only shear, they can't open. So it's showing a much, much exaggerated EDZ, quite different from UDEC at least, and I think it's different from the reality. A long time ago, we did some physical models before UDEC came along, physical models of large span caverns for nuclear power plants underground, 50-meter span caverns. So this is where we got the idea of the big caverns, and wouldn't it be nice to have a big cavern in Norway? And finally, the Olympics gave that opportunity. So I had the physical models that looked like this with the loading frame and could generate fracture sets. Okay, the last topic, the last few minutes, safe rock slope angles, and a little glimpse of Q-slope for numerical analysis. So are these slopes in Indian Kashmir, where Northern Rail was developing a lot of tunnels, are they stable? Is it nonlinear shear strength? Is it high total friction angles? I wouldn't personally park a car where those cars are parked. I mean, I'm not so trustful of the high friction angles. So we have Q-slope now, thanks to a lot of case records collected by a colleague of mine called Barr. And the idea is that Q-slope, it gets larger and larger, and your slope angle can increase more and more. So you see the values in the middle there. Q-slope 0.01, slope angle 25 degree. Q-slope 1, 65 degree. Q-slope 10, 85 degree. So lots of case records. It's basically the Q formula with some modification for slopes. I don't know if any of you have tried it. And you can have a different JRJA weighting on each side of a wedge. So do we do slope stability analysis with continuum or discontinuum assumptions? We have the classic figures from Hook and Bray from that very nice book about slope stability from 76, I think. And the other diagrams are actually from my thesis, also showing a possibility of circular failure. If you have really disintegrated rock, circular failure is certainly happening, but in general, it's not true. So these I don't believe. This is artificial. It's rock is given there a compression strength of 20 MPa. I don't think rock slopes can fail like that. And they can't fail like this. This rock is given 78 megapascal compression strength. It's an impossibility. They're artificial ideas of circular failure from geoscience, Hook-Brown modeling. They don't exist in reality. This is a set of descriptions of the reason for major open pit failures, and very few cases with structure not listed are shown, just a few in the blue ones, yeah? Nearly always joints or faults are mentioned. Our case records, they show wedge failure, plane failure, toppling, and very, very, very few circular failure. On the left, it really looks like circular failure, probably very weathered soil and rock. Circular failure, yeah? On the right, it maybe look like circular failure, but it's actually not. It's actually a fault plane 200 or 300 meters long. That's the major cause of that progressive failure in the Bingham mine in the USA a long time ago. So finally, I have an idea for a progressive failure criterion. So the intact rock, the pink, has got real cohesive strength. That's the failure of the intact bridges. And then these new fracture surfaces, they shear, the orange, the yellow, the fractured rock. And then joints may be mobilized, the green. And there might be some faults involved, one side of a big wedge, for example. That's a very typical failure in a big open pit. A joint set and a wedge from a fault zone. So I have this criterion that's called CCSS. It's actually a soundbite. It's crack, crunch, scrape, swoosh. Crack is the intact bridge. Scrape is crunch is the very rough surface being sheared at a little bit more strain. Scrape is any joint set, and swoosh is a clay-filled, maybe water-bearing fault. So CCSS, if we could just decide how much of each component, we'd have a criterion, because we have equation for each of those components. So what do we learn from continuum model? I don't think so very much, and that's the end. So this is a pre-injected tunnel, had a big leakage range, Lujon 0.1 to 370, and after pre-injection, very, very small inflow to the tunnel. So I hope I haven't used too much of my extra time, but thank you for your attention. I can go down now, or sit here. Sorry?
Need to facilitate you.
Okay.
Thank you, Professor Barton, for such an informative keynote lecture. It really sets the scene for the conference. I now request Dr. Agarwal to kindly felicitate Professor Barton with the memento.
Okay. Thank you very much. Thank you. Nobody's taking picture. Yes? Okay.
We have got a small information. There was a bag which was given to one of the delegates from L&T. If someone has the bag around you, can kindly check the bags, because all the bags are of same shape and same size. So some bags have got interchanged. I request you to kindly check your bags. If you have, if the bag is from L&T, kindly give it to the person. You can contact Lokhande sir. He will redirect you. The bag contains Ray-Ban glasses in the side pocket, so you can just, it'll be easier for you to spot it. So we'll continue our keynote lecture. Our next keynote speaker is Professor Deb. It gives me a great pleasure to welcome Professor Deb to deliver the second inaugural keynote lecture. Professor Deb is a professor of Department of Mining Engineering at IIT Kharagpur and a leading expert in mining and mineral engineering research. He is currently the president of ISRM India. He obtained his bachelor's in mining engineering from IIT Kharagpur and his MS in mineral engineering and PhD in interdisciplinary mining and in engineering mechanics from University of Alabama, Tuscaloosa, USA. Professor Deb has international academic and research experience, having served as an assistant professor at Southern Illinois University, Carbondale, USA, and as a visiting researcher at Korea Institute of Geosciences and Mineral Resources, South Korea. His outstanding contributions to geosciences and mineral engineering were recognized with the prestigious National Geoscience Award conferred by the President of India. He has authored 4 books, holds 5 patents, and has published over 200 research papers in several reputed journals and major national and international conferences. He has supervised numerous PhD scholars, 2 of which are my colleagues. I am very proud of that, contributing significantly to the academic leadership and research in mining engineering. As stated earlier, Professor Deb is currently serving as president of Indian group of ISRM. I request Dr. Lokhande to kindly welcome Professor Deb with a bouquet. I request Professor Deb to kindly enlighten us.
पॉइंटर लगे नहीं, इधर से बोल देंगे। अच्छा ठीक है, दे दो। Very good evening. I am standing in between your dinner and the lecture, so let me see how quickly I can complete. Okay, the first 3 slides, I will be acting as a president of ISRM, of Indian group of ISRM. So, the reason I have saying this, the rock mechanics is going on for a long time in India. However, if we see our membership, the characteristics or the composition, it's mostly coming from the civil side. So, I thought that in mining, so much of rock mechanics is being, practiced, but the membership is very less from this side. So this is a really call for that. So those who are working in this area, I will strongly encourage you get a membership. You get a lot of benefits. Some of them are listed here. And the objective of the society is basically the international collaboration, just like you have heard Professor Barton. So like this, we organize also international conferences, and not only that, you can get a lot of discount when you go for international conference or even national conferences under the banner of ISRM. So having said that, I think we have a booth right outside there, and if you have not done that, it's just a click of a button. Now just a Google form has to be filled and you can become member instantly. So I want, since I belong to the mining fraternity, so I want more and more mining person to be involved in this society. So thank you very much. So now I come to the keynote lecture, and I can tell you that it is my privilege to share dais with Professor Barton. And after this such an informative lecture, I do not have much to say, just to say that we teach the students and Professor Barton teaches us. So that is the difference. But what I thought I am going to do in this keynote lecture is just to give you a brief overview. I'm not going to delve into the technicality of each topic, but you will see a glimpse of topics coming up in this lecture. So that's why I given the slope analysis, monitoring, stabilization, everything is combined. So I'm going to tell you what is going on all over the world and where we are heading, and as far as slope analysis, stability part of it, then the monitoring part of it, and also the stabilization. So what are the concerns? Mainly in mining side, if you see, there are 2 types of slopes. One is pit slope and another is dump slope. And these days we are more concerned about the dump slope than the pit slope, because that is where majority concerns are there and failures are happening. So the constraint in Indian scenario is the space. We know that is the major constraint, especially for dumping. And also for the development of the pit, either it's open cast or open pit. Our land is very much constrained because a lot of villages are around. So under this constraint, the companies are working. Second is geological variations. I think in the Professor Barton's lecture you have heard. Stability and these days this sustainability is a key word. So that is also a big challenge. And the solution is definitely the monitoring is one part. Either you call it due to vibration or plain failure of the slope. So the implementation, what everybody is now looking for, whether we can get a very IoT-based, fingertip solution, that we need to know that the cause of that or the situation changing rapidly, and we need to know also very quickly as far as possible. So the IoT-based solution is probably one of the solutions the people are going into. So the open pit slope, now general, what is happening in this country is the pit slope may reach, in some cases already reached, 400 meter. And internal dump height are already planned 450 meter. From this is for the internal dump. External dump is about 150 meter right now, the height of that. And the pit widths are going more than kilometer. So this is the dimension we were talking about. And they are full of geological disturbances. Then water, definitely a big issue in many parts of the country. And so the water management and the stripping ratio is also a issue in many mines. These are some pictures where we have worked. Mostly the picture what I will show where we have given some solution. So this is from iron ore mine. This is a mine in Goa. And you can see the amount of water in the right-hand bottom. The iron ore, the ore body is below that, below 2 benches below. So this is the manganese layer, and this was very much just like sand. So this is kind of situation of the slopes. Now if you go by this is a pretty crude definition, I think all of us know, that bench angle is a concern, that what will be the height, but we are mostly concerned about the overall height rather than the bench height. But if you have to observe each bench and how the joints or other factors are there. This is a very scary picture. If a mine has this kind of the rock mass, then definitely what they need to do. I think there are two ways to approach. One is you see the single joint and you find out the joint which are most critical, or you go by a classification system like Q or RMR and you think it as a big mass. So if you are going by the single joint, like a planar failure in a pit slope case, then we need to know these three parameters, some geometrical parameter, then their measurement, the aperture, all this good stuff we have to do in the field. We find out the orientation of those, and then we reduce it by 1 dimension, sometimes 2 dimension, and we go into the pole, and we understand this, what is the orientation and orientation of our slope vis-a-vis the orientation of the joints, the most critical joint. This is not exactly sorry. Oh, I came all the way. Oh. So this right-hand side figure was a very critical mine. This was the iron ore mine, BHJ, I think it was. But what they have done is they made a high wall because there is no space. So they made a high wall where the width of the bench finally become almost 1 or 2 meter. And then in the bottom, they want to build a structure. So definitely it's a concern that the overall bench angle become very high, more than 60 degree. So whether that will be stable, so we did some work for that. Oops. It should be, there are more slides in between. Why it is coming like that? तो लास्ट में आ गया. Can you restart again? The version problem looks like. No. Oh, this has somehow come. Okay, fine. I'll come back to that 2 slides later. So those are the pit slopes. So if you want to analyze pit slope, one is by finding out the critical joint vis-a-vis to the orientation of the slope face, or just now Professor Barton has said about Q slope. So you can find the safe slope angle and go by this Q slope method, or there is slope mass rating. So in India, this is one of the most prevailing classification system for slope. But I can tell Professor Barton that the Q slope are gaining popularity. And now, in fact, I have advocated recently in Jaipur, there is one conference organized by DGMS, that we should also go for this Q slope. So they may make a circular on that, along with this slope mass rating. So this is based on RMR, and there are some 3 more parameter based on the angle, and also the water condition and all this stuff. So either you go by the classification system and you find out the safe slopes, or you get a particular critical slope, critical joint, or a discontinuity, and you analyze based on that. So these are the 2 options we can go by. For the overburden dams, as I told you, the maximum dam heights right now restricted to 150 meter in general, but if somebody can prove it can be more than that, then they will allow. The material is mostly granular. It's like a SRM type of material. And the size varies from micrometer to meter. So it's a very wide variety of boulders you are getting there, from sand to more or less big boulder. So the understanding the material property is one big thing for the dumps, and it is wide and is very large. So in the laboratory, we can only test a particular size range, and based on that, we have to guess that what is the property that could be in the field. So recently, we have developed a machine which can test in situ shear properties like cohesion and friction angle. So that probably gives much better way than bringing the sample to the lab, because it's very difficult to maintain the density the moment you disturb that. And our experience shows that the naturally compacted dump, we are not able to make it in the lab. When we check the density in the field, it is about 2.2 to 2.4. But we could not achieve it in the lab. We tried many different ways. We could go up to 1.9. So the nature makes this compaction much better. And since the compaction of the density, we are not able to match. So the extrapolation of the results, like cohesion or friction angle from lab to field, may not be the accurate. So that is the one of the reason that sometime the laboratory tested results doesn't work in the field. So these are again dump, those we have analyzed and tested. So here characteristics I have already said, and what we need to find out the permeability, porosity, if possible, and the shear strength properties, either in the lab or in the field. But I'm saying that field is better, but it's very cumbersome to do those tests. It's not so easy. But nonetheless, we have to find out a very close value which may represent in the field. So I think those are the failure portions. Now the analysis. There are n number of softwares available. Some are limit equilibrium concept, and which for a dump case it will show you, because it's a granular thing, it will show you like a circular failure. So based on either Bishop or other methods, Jambu methods. So this is for granular material like dump material. We are comfortable of doing this. This is one case study which we went later, because failure has occurred, and then only after that only we were called. So I have a small video also I can show you. So this has gradually, basically this is a coal mine. So the dump was placed in the decoal side, in the rice side. And one fine morning, this entire thing was started moving. And it went by stage. The cracks were happen stage by stage. And it took about 7 days. This entire material came to the where the working was there. So like that, the failure started, and then finally it came all the way down where the working was going on. So this was in the rice side, so it's gradually moved. But it's given them almost 7 days, so they could move everything. Okay, it's not so fast. So you can run the video, for just 2-3 minutes. So they had a long video. I just cut a little bit how the crack has happened. And the people are standing on that dump, which is moving, and they're taking pictures. So that was interesting. Okay, you can stop now. So that's one side. And then the second, the type of analysis is the numerical methods. Continuum based, discontinuum based, you have many choices. Definitely discontinuum based will be the best choice. But these are, what I'm showing is the continuum based model. They are either based on FEM or FDM or other methods, the continuum based methods. And there are many methods are coming up. Even some are particle based methods like SPH, PFC. Although they use continuum based formulation, but they are not grid based. So those are also available now. Now this is another method which is being It's probably better, but I have no experience on this, but this is from a paper I have given. Discontinuum base, so this is DFN network, so you have to have a software like UDEC type software, where you can actually model the fraction network, and then it will give you the safety factors or the stresses, displacements, whatever you require. So what I'm telling you that there are n number of options are available. Now based on your study area or your requirement, you can choose one. And these days, the software companies are very clever. They are even giving you you do not have to purchase the software. You can just get the license for a month also. So it's much cheaper. You can just get it. If you think you can finish the work within 1 month, so you can do it. You just take a license for 1 month. So it is very, very clever way. I think it is also good for us. Whenever we require, we get that license and do the work. Now, I already mentioned that there are n number of softwares available which can do the slope stability analysis. Now, there are continuum, discontinuum, many 2D, 3D, many options are available to you. With water, without water, with dynamic load, without dynamic load. Means there are n number of choices are available. You choose which one you want. So I again listed it, whatever is available. Now, these days we know the AI is coming, and there are many authors who are trying to get AI into the slope stability. It's not exactly the classical mechanics type of analysis what AI is doing. It's the history matching, or see this side, they are finding out the relationship if you have many data, because AI is run by data. So if you have a lot of history data, then the AI can be used to understand, those various things. The relationship between two parameters, or you classify the slopes based on their height, bench angle and all this stuff. So they are not doing just like what FEM or FDM will do, but there are some options available if you have many data. So you can classify and you can find out this type of slopes are more vulnerable to failure. So this type of analysis are available these days. So these are more or less where the slope stability analysis is going on. Now if you see the monitoring side, the best one is so far, probably to me, is the rudder based, because it can take the wide area, and there are very good software they have developed, and based on those data, almost real-time analysis. So it is monitoring almost more than a kilometer area range and the entire height of the benches. So this is available. On top of that, you can use numerical analysis. So it's hybrid method. You are doing numerical analysis as well as verifying with this monitoring data. And then you are coming up with whether this slope is going to fail or not. So these are new technique which is coming. So they are merging digital photogrammetry, satellite radar interferometry, and then geomechanical modeling like classical techniques. So they are combining everything, and some papers are coming up in this area. So what I'm saying is some people are focusing in merging monitoring and modeling together and coming up with the results. Then some drone-based method, then SAR-based method. I think these are some techniques which have already established or is going to be established. But in our country, more or less the ground-based radar, which is giving results, and many mines have already been installed them, and they are giving them the results. Apart from that, we have classical system like total station and putting the pillar and doing the classical survey. Those are already available. Another technology which is being used for monitoring is LiDAR. In some of the mines, they have installed it. That is also looking at the face continuously. And for any movement, they are giving the results. This is one technique which may be cheaper in pretty short period of time, but now still it is expensive. It's the fiber optic sensing. It's a fiber optic which can measure the strain and at a distributed points. So if you can, but it is a contact base. It will not be a non-contact. So you have to install that in your slope. So that installation is the critical here, that how it should be attached to the slope, that need to be seen. So it may be grouted or something we need to do, but you can monitor almost 50 kilometers in one go. So this cable can be laid down 50 kilometers, but it must be distributed. This distributed thing is now a little bit costly. So this every 2 centimeters you can measure the strain. So you can think, if it is every 2 centimeters, how many sensors in 50 kilometers you are monitoring simultaneously? So I got intrigued by this. So there was one German company who approached, and I asked them to come to my lab, and I really want to test it. So I got it tested. So this is the fundamental. I'm not getting into that. So this is what I did is I put in a bolt and I grouted it, and then I pulled the grout. So the cable length was pretty big, but my bolt is only was 0.3 meter. So you can see this graph. Wherever I have, this is where is the bolted portion, and this side is that you can see that bolt where the cable was installed. And this is what is the strain we got when we started pulling it. So it's really worked. It only shows the strain has occurred in there, and all other where nothing has happened. So that means this technology is very good. Even if you can measure up to micro level, because you say what the measure is the change of speed of light. With the moment it gets stressed, the speed of light will change inside that, and that is what they are measuring, and it just works. So if now we can place it all around the mine for some way, then wherever that strain will come, and then we will know this is where the movement has started. So this is good technology, but I think still it is expensive, the distributed one. But there are 3-4 players already are available, so I am seeing because of their competition, the price will go down. On this matter also, I talked with DGMS, and they said we have no problem. You can go and install it. There is absolutely no problem, because they have no issue. Now, if you are using this, let's say, ground probe, the radar or the fiber optic or whatever, LiDAR, you are generating volume of data per second, huge volume of data. Now it is almost impractical that a person is going to look into that data and say something. So we need these technologies like AI, ML, whether we like it or not. We need to have these technologies to find out that, and we have to develop some algorithm that what do we want. If we want to find out some problem in some area, how we can extract that from this data. So this need to be done, and I see this is one of the big future of our young engineers or young researcher, that this is the area, even in Coal India, they have multiple places these ground probe radars are installed. I can guarantee you, no analysis is happening. It just, the volume of data is lying somewhere. Nobody is looking at this. So if somehow, even today the CMD has said, even one of his mind, it is there. I know that. But if he allows this data to transfer to us, I think we can do many things. So this is one of the challenges. And there are a number of techniques available, and our young researchers, they know all about it. You know, ANN, CNN, SVM, whatever you call it. They know all about it. And those data are waiting to be analyzed and tell something, some information which will be very useful to the mining people. One such method I just tried with one of my students, but it didn't take their data. What I did is, I asked the student, you take lot of pictures of a dump. And he used deep learning. And we could identify after that, from the same dump, of course, we took picture and it told the size distribution of that, the boulder size distribution. So he analyzed almost 500 data before, and then you take any picture of that dump, and that will give you the size distribution at least. Then what we have done, we took the sample to the lab, and we tested the shear strength properties like friction angle and cohesion. And then based on the density, we try to say whether we can now forecast based on the density and the distribution of particle, whether we can forecast that CN5 for the field. It's a very long way to go, but we have at least initiated that whether AI, ML, whatever methods they are saying, whether this can be make a bridge between field and the lab. Because we have to finally go back to the lab to find out the basic properties. But we need to have the information of the field. And that bridge, can this AI, ML can do that. So that was one of the approach we tried. And then there are n number of stabilization methods. I am not going to bore you with this. You already know. The geogrid, geocell, all this stuff are already there. How to manage the water. These are some good stuff for the field people. May not be to the researcher, but they actually record this. When we visit to the mine, we see there is no drain. Drain is choked, And only once the mine started getting a lot of water, they think, oh, drain is not there. So, these are very simple things to do to avoid a disaster. And we should do that. It should be in the SOP somewhere that monsoon is coming and we should be preparing this thing, 1, 2, 3. So I'm not getting into that because I think dinner is waiting. Vegetation, this, that, you already know. So the final conclusion is that we have to know our geometry very well and our material very well. Geometry 100% we know what we are dealing with. Material, probably not. Okay, I don't know how much percent, but maybe if we can come close to 50, 60%, we understand this material, we will be very lucky. Other than that, the joint bearing plane, the geological information, everything need to be gathered. There also we are lacking, in fact. You know, these geological studies, we hardly do. You know, Professor Button is saying Q system or some is saying RMR system, but they all need data. And you need to go closer to your face, to the slope, to get those data. So that somebody need to collect. And this is a dynamic process. I cannot do once and say it is done. You know, most of the time if you go and ask, what is the value of RMR? The entire mine of 1 kilometer, they will say one value. You know, 56. So this is how, you know, cannot work that way. Well, so someday disaster will happen. So this is where I think I need to say, and there are n number of techniques are already available. We need to find out which one is appropriate for us. For that, maybe people like us may help you, that this is the technique, or this is the methodology, or this is the software is good for you. This is the approach you require. So thank you very much. This is what I had to say. Nikadu? Oh, podium. Oh, you will use podium, right.
Thank you so much, sir, for the enlightening lecture. It was very heartwarming to hear AI being mentioned, especially the new age is AI. So I'm really, really grateful for this wonderful keynote lecture. I now request Dr. Lokhande, Conference Chair, to kindly felicitate Professor Deb.
Thank you.
Thank you so much. Yeah. Now I invite all of you for the dinner and the cultural program. It is awaiting you in the convocation hall, convocation lawns. Thank you.